So hello all, I welcome you in this video. In this video, we will see the working of a forward converter. In the last video, we have seen the flyback converter, and flyback converter is basically there are the two circuits which are electrically isolated from this high frequency ferrite core transformer, and the orientation of these two magnetically coupled inductors are opposite to each other. And in this way, we have designed the flyback converter. This is the smoothing capacitor connected across the load resistance R. And here V naught appear across the load resistance R. This is C, this is G, this is L1, this is L2, this is the MOSFET, and this is the V in. And here the V out is equal to V in into D upon 1 minus D into uh, Ns upon Np, where Ns and Np are the number of turns in the coil 1 and coil 2 and coil 1 respectively. Now this forward converter, how it is different from the flyback converter. So the major difference is when this switch is off, then there is the burden on the transformer to supply the energy in the secondary circuit. But in case of forward converter, what is the modification? Let us see. So number one modification is here, instead of using one diode, we are using two diodes which are connected like this. And here we are using the inductor, and its job is to store the energy when the switch is on, and its job is to release the energy when the switch is off. Again, this is very small size capacitor, only for removal of ripples from the output voltage. And this is the load resistance R. So let's say this is D1, this is D2, this is C, this is R, and across this R V naught will appear. So, and this is the high frequency switch MOSFET. So what is the difference? Difference number one, here we are using two diodes connected like this. Number two, we are using the energy storing inductor. And number three, third difference is the orientation is same. The orientation of the coil 1 and coil 2 over the ferrite core high frequency core is same. Now, what is the output voltage? So output voltage is related to input voltage by this relation. V naught is equal to V in into the duty cycle into Ns upon Np. Okay, this is the expression between the output voltage and input voltage. So let us see the working of this converter with the help of waveforms. So first of all, this is the switching cycle. This is the on time. This is off time. This is on time. This is off time. On time, off time. Okay, so this is on, off, on, off. Now, let's say this is the primary current IP, and here we will draw some current IL, and this is V naught, and this is the polarity. We will see that this is V1, and this is V2, and this is V in. So, what happens when the switch is on? When the switch is on, when the switch on, let's say this is the mode 1. So during this period, the IP current, the primary current will flow through the coil L1. So this is the primary current, and it will increase from a minimum value to maximum value. Actually, pattern starts from somewhere here. We can start from zero means, but since it is very high frequency, it before approaching to zero, the next cycle starts. That's why we start from somewhere here, the I min to I max. So this is increasing from I min to I max. Then it is zero. Then no current. When switch is off, no current. Then I min to I max. Then no current. Then I min to I max. This is the variation of current, primary current. Now in the second mode of operation, when the switch is off, then what is happening? So during the on period of the switch, the polarity of induced voltage across the L1 is like this, plus minus, and since their orientation is same, so V2, the polarity of V2 is like this. and here the current will flow, and this plus makes this D1 forward bias. This plus makes this D1 forward bias. So when the switch is on, D1 is forward bias, and IL flowing in the inductor, and it will simultaneously it will store some energy, and it will appear some voltage will appear across this one, that is VL. So if we plot the that IL, so that IL will gradually, the voltage will gradually, the current will gradually increase, and when the switch is off, so when the switch is off, then what will happen? The polarity of voltage across L1 will reverse, so it is plus, this is minus, this is the V1. When the switch is off, this is the polarity, and this is the polarity when the switch is off across the L2. And this this makes this D1 stop conducting. So here the D1 is reverse biased, and D2, since plus makes D2 forward bias, and the conduction of current through the load is continuous, and the polarity across the inductor will change to maintain this continuity of current through it. So we can see the during the off period, there is burden on the transformer is less as compared to the previous case. This L1 is sufficient to maintain the continuity of current, and will appear the voltage across the output during the on time and off time also. And this L and C will contribute for this load current during the off time. So how to draw the waveform of this IL? So during, when the switch is on, it will gradually increase. When the switch is off, decrease, then increase, then decrease, then increase, then decrease. Now let us talk about the uh, output voltage. So we have seen the output voltage appears across the load when the switch is on, as well as when the switch is off. So the behavior of output voltage across the load is same. I mean, when the switch is on, there is the voltage. When the switch is off, there is the voltage. There is the voltage. There is on. So the on output voltage is a regulated DC, and it is related from this relation V naught is equal to Vn into duty cycle into Ns upon Np, and it appears across the load when the switch is on as well as when the switch is off. So the advantage is that the copper loss in the transformer is less, or the losses in the transformer is less, and drawback is, since the inclusion of these two devices, the cost is pretty higher as compared to flyback converter. Okay, so thank you for watching this video.